Hello Abaqus users. In this video, we're going to make an introduction of heat transfer analysis and also define steady-state and transient heat transfer analyses in Abaqus along with some examples. So stay with us.
In this lesson, we will study and teach a very important topic, which is heat transfer and thermomechanical analysis. The first step is to explain the types of heat transfer issues. One of them is uncoupled heat transfer analysis. In this type of analysis, you can have thermal analysis without mechanical analysis. In fact, you only have one heat transfer analysis. Another type of these problems is the sequentially coupled thermal stress analysis. In this method, thermal analysis can be performed on a model with mechanical boundary conditions, and the results can be seen properly. In the third case, the thermal solution must be performed simultaneously with the mechanical solution. In adiabatic analysis, temperature is actually an output, but not a degree of freedom. The details of each of these methods are given in the following. In uncoupled analysis, the temperature field is investigated without considering the stress field and deformation. This method includes conduction, boundary convection, and boundary radiation. Thermal problems will be divided into steady-state or transient, and can be both linear and nonlinear. In the transient state, changes are made over time, but in the steady-state method, we reach a stable state over time. In this method of heat transfer, our solver is Abaqus standard type. You see the types of situations where heat transfer can occur. The first case is conduction, in which we actually have two walls with different temperatures. And heat is transferred from the wall with the higher temperature to the wall with the lower temperature. In the second case, heat transfer occurs between a solid surface and a fluid. Due to the fact that the surface temperature is higher than the fluid temperature, heat is transferred from the surface to the fluid. Finally, the third mode is radiation. In the presence of two surfaces with different temperatures, heat is transferred to surrounding. Here we describe two modes of heat transfer, transient and steady-state. In transient mode, the overall heat transfer rate is equal to the sum of all heat transfer rates in different modes, as convection, radiation, conduction, and dissipated heat or any other types of heat. And this sum is equal to the change rate of internal energy over time, rho multiplied V multiplied C multiplied delta T divided to delta T. Rho is density, V is volume, C is heat capacity, and delta T divided to delta T is temperature variation to time. In a steady state, the solution is done by adjusting summation of heat transfer rates to zero because there is no temperature variation in any time period. To simulate the steady state mode, we have considered a two-dimensional screen. Desired output value of each element. To see the temperature in different nodes, we do the same. but set the probe to node mode. In order to see the temperature exactly on the desired node, the distance must be selected from the Query tab again. And we must find the distance from the bottom edge equal to 0.2 to reach a point and read its temperature value. In this section, we want to simulate heat transfer as a transient step on the same previous model. You see the constant values required for this analysis. In this case, 2, the goal is to find the temperature variation at E point. Given that in this analysis, according to the equations, we will have a change in temperature over time. So it is necessary to consider the density and a specific heat in this time. If we go to the job module and look at the results, we see how changes occur over time. Now we show that in this case, over time, the temperature reaches its value in the previous analysis at the same examined point. First, in the XY Data tab, we enter the Create, click on ODB field output. Here we select the unique nodal and then activate the nodal temperament option. In the Element and Nodes tab, click on Pick from the viewport and select the desired point on the model. And in the XY Data section, we change its name to Transient. In the next step and in the job module, we open the job called Steady-State and save the result of the same point in this analysis. We change its name to Steady-State. Given that the transient analysis time is 15,000 seconds, we must increase the duration of the steady-state results to 15,000 seconds to see the results simultaneously. Select both modes and draw the diagrams. Now we see the expected result. In steady state, we have In this workshop, we are going to simulate a fully coupled thermal stress problem. This is a forging problem and the axisymmetric elements are used. Because we will get a lot of strain changes, we are using the ALE method. In this workshop, both the coupling method and the ALE method will be fully explained. The geometry of the punch and sheet is clear here. The punch pushes the sheet from both sides, so because of the symmetry, half of the model will be simulated. Also, because it is completely symmetric in terms of loading and geometry of the model, we model with the axisymmetric method. The coordinates of the die points are specified here. And in order to avoid the stress concentration, we build edge fillet in the die vertices with the specified radius. In this problem, we will use SI system. Model mechanical specifications are outlined here. Inelastic heat fraction coefficient stands for the amount of plastic work that will be converted to heat during the process. Yield strength depends on the plastic strain, strain rate, and temperature are specified in this table. Temperature-dependent elastic specifications are also listed in this table. Because it's a coupled problem, so the mechanical specifications are temperature-dependent. And because we use explicit solver, then we have to define density. In addition, we need an inelastic heat fraction to convert part of the amount of energy generated by plastic deformation work into heat. Here are the interaction specifications between blank and environment, such as convection on right edge of blank. We also have heat transfer radiation from both sides of the blank, the specifications of which are listed here. Because it's a coupled problem, so you need to define the Stefan-Boltzmann coefficient. Because blank and die collide, so there is heat transfer between them. The conductivity and clearance full. To do this, from View, we select the ODB display option. In Sweep Extrude tab, we tick sweep elements and adjust the angle from 0 to 360 to see the full model. Notice that this model is still half. That means the underlying half is not displayed here yet. The rigid object can also be fully observed by checking the second checkbox. To see the inside view of the model, we sweep the model from 0 to 180 degrees. This is how the stress changes in the model. Now we want to create symmetry over the XZ screen to see the model in full. First, we return the appearance of the system to its original state. Then we use the Create Coordinate System and create a fixed system. Determine the center of the coordinates system, then select the direction of the X and Y axis. Now we go back to the ODB display options and first sweep the model. And then we go to the Mirror Pattern tab and mirror the model relative to the XZ plane. Remove punch so that we can better see the results for blank. We use the Common Plot Options tools and remove edges of elements. In this workshop, we are going to simulate a collision of a bullet into a rigid flat. The purpose of solving this problem is to use theories such as Johnson-Cook theory for the plasticity and hardening, as well as the use of Adiabatic. In this problem, by examining velocity changes, we predict bullet behavior. We also examine how changing in impact time affects dynamic problems. Note that the problem is completely dynamic. The initial speed and temperature are 228 degrees Celsius. The diameter of the bullet is 6 mm and its length is 30 mm. Because the model is symmetrical in terms of loading and geometry, so we use 3D elements, and we model only a quarter of the model. The mechanical properties of the model are as follows. It's not a coupled issue, but because it's a adiabatic and there are heat issues, then there is a need to define parameters like inelastic heat fraction and specific heat. The Johnson-Cook relationship is brought here to get the yield stress. The main relationship is in the first parenthesis. After meshing and submitting the model to solve, we see the results for the model. Parameters such as the stress, equivalent plastic strain, and so on can be found for the model. To complete the model, as before, we first create a fixed coordinate system. And mirror the model by the symmetry planes. In this problem, the symmetry is relative to the XZ and YZ planes. Plot kinetic energy values during the solving process. Because we only have one part, kinetic energy changes are the same as bullet velocity changes. However, the speed varies in different elements, and this amount of values is a kind of an integration on the whole model. Now, if we want to see the speed chart for the bottom of the bullet, we need to remove the mirrored images first. Then we read XY data from ODB field output and select magnitude from the velocity subgroup.
Hello everybody and welcome to our new video training package of Abaqus, Thermal Heat Transfer in Abaqus. This package includes these sections: Introduction to Heat Transfer Analysis, Steady-State Heat Transfer Analysis, Sequentially Coupled Heat Transfer Analysis, Coupled Heat Transfer Analysis, ALE, Adaptive Meshing, Adiabatic Analysis. Thank you for taking the time to watch this video. We hope it will be useful for you.